Alright everybody, so now I'm going to be talking about the mechanism for the reaction of the addition of water to an alkene. So this is an electrophilic addition reaction, and that does form a carbocation, so rearrangements are allowed. And the alcohol that you see here actually adds Markovnikov, which means that, well, actually the water species as a whole, you would say, adds Markovnikov, which means that basically the hydrogen adds to the carbon bond that has the least substituents bonded to it. So the carbocation basically goes on the most stable carbon, sp2 carbon of the double bond. Alright, so with that out of the way, basically what there is to understand is you need to understand how nucleophiles and electrophiles work, and you need to understand curved arrow mechanism, or I guess just electron notation via curved arrows, which is part of all of the mechanisms basically. And in this instance, it's actually going to be, since it's just electrophilic addition reaction, and these are basic, it's just going to be a double barbed arrow representing the flow of 2 electrons, which I'll show in a minute. But yeah, and so there basically forms a new sigma bond, right here, bonding this carbon to this oxygen, and that's basically the whole thing about these reactions, right? Okay, so, and the hydrogen off of the other carbon from that original double bond right there, right? Okay, so getting started, you'll normally see these reactions written sort of like this, right? Or, sorry, I apologize. That's completely wrong, actually, what I just said. No, you'll see them written like this, right? And so you might be thinking, and your textbook might even show, that the H2SO4 is a species that donates a hydrogen. And that's partly true. But in reality, we know already that the hydrogen, or this is actually sulfuric acid, but this is a very strong acid, and so it's just a catalyst, really, in the solution of the water. So the hydrogen from the sulfuric acid gets abstracted, and it protonates the water into H3O+, which is hydronium ion, which we see right here. Because this is just, it's a strong acid, it's a simple acid-base reaction. We can see from the equilibrium arrows here that it is strong to the right, or to the products, producing hydronium ion, right? And so that's what happens, but which I actually show in the mechanism because that is crucial. There was a time when I was first learning this mechanism that I didn't really understand that, because my textbook, like I mentioned, showed just H2SO4 being the hydrogen donor, but we'll see that that is not necessarily true. But it just shows that because you're not always going to have water, you might have, CH3OH, that's methanol, or something like that. So you'll get used to just doing the acid-base reaction like in your head. You don't need to really draw it out every time, but it just makes it much simpler to understand with the actual species that you have, whether it's water or whatever, what the actual reaction is doing. And then because that's really crucial for what your final product will have. Anyways, let's get started with the mechanism. So I drew this one in green, and it's a little confusing, but I'm going to walk through it. So, we have this as the starting material, right? And then this is the product. And so the first thing I always like to do for these reactions is just count my carbons and everything, which will become important later in the semester when you're learning more mechanisms, but right now not so much, but it's just crucial to do it anyways. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? So we're good there. And of course the other one up here, but we don't really need to consider that one since it's not part of the main chain. So we see here, this is H3O+, and basically a hydrogen, this double bond right here is the nucleophile, right? And then this hydrogen is the electrophile in this step. And so this double bond is going to donate some electrons here, 2 of them, as seen by that double barbed arrow. And it's going to attract that H, and then it's actually going to break off of this oxygen right there. And then onto the second step here, we have this water molecule that is still in solution, which I know this acid-base reaction right here doesn't show it the best, but it is still in solution, right? And so that's what's going to be attached, or really attacking, that carbocation right there, which, like we said, it's Markovnikov, so it's going to be on the most stable carbon. And that's just because of hyperconjugation stabilizing this, because, you see there's 1, 2, 3 alkyl groups on there, which donate electrons via sigma bonds to that carbocation, so you're just sharing the electron density throughout. So it's more stable, because we know that So then, down here at the next step, after that water, this is water right here, adds, there's going to be a positive charge, which you can see right there, on that oxygen, right? And so then we have another water in solution, pulling off this hydrogen right here, and then this is the little curved arrow right there, demonstrating that these electrons are going back to that oxygen, right? Perfect. And then that eliminates that that eliminates that positive charge on that oxygen, so we see there's nothing there. And that also regenerates the acid, because that's very crucial for all of these reactions. You're going to regenerate some acid. And that's just understood for these reactions, really, so we don't need to demonstrate that up here. We don't need to denote that, but that does happen. Okay, great. So, moving on to carbocation rearrangements, which I mentioned up here, do happen because if a carbon with a positive charge can rearrange that positive charge to another carbon that's adjacent to it, only one carbon away, to be more stable via these stability rules right here, then it will happen. Only if it's adjacent, though, which in this instance it will be, but if you're not going to have something like a carbocation on one carbon here like this, like a carbocation down here, and there's a hydrogen here, which, yeah, that could move over to here over time after this hydrogen moves and everything, and then this hydrogen moves, but that's not going to happen because it just needs to occur in one step. So if I were to have something like this, where the carbocation was there, and there's a hydrogen there, of course this hydrogen is going to go there, which will then generate, oops, I drew that in reverse, the hydrogen, or the carbocation there, and the hydrogens off of there. And that's just because it's one away. It's right next to it, it's adjacent. So, yeah, that's what happens there, and that will be seen in this problem here. So let's begin. So again, same thing. I didn't draw the acid-base reaction for this question just because I used the same exact reactants for this question, so I didn't really feel like it was necessary because we already have that right here. Perfect. So then basically that hydronium, same thing. The hydrogen gets abstracted right here, and then we have a carbocation right here. And because we see that it can become tertiary right here versus secondary right here, we will get that 1,2 hydride shift, which I mark right there. And these are the main two types of shifts you get: 1,2 methyl shift and 1,2 hydride shift. Anyways, then the water again adds and then gets deprotonated down here, just like it did before. Perfect. So yeah, these are just some notes, which I already said. Like the carbocations will only shift to become more stable if it can shift over by one carbon that's adjacent to wherever the carbocation is. So yeah, I mean, the biggest thing I would say to memorize this mechanism is just understand at every step the nucleophile and the electrophile, right? Understand that And it's also crucial to understand this acid-base reaction because when you actually have to draw out the whole mechanism, you could get the products by just saying, okay, well, it's H2O, I know it's going to be just one hydrogen off, like less than that. Or if it was CH3OH, then of course it's just going to be CH3O with the O bonded to the hydrogen or to the carbon, the final product. But when you're asked to draw a mechanism, like on a test, you need to have this deprotonation step. So that's why that's so crucial to understand that acid-base reaction. And then, of course, just the Markovnikov addition aspect. That's also very crucial. And so, yeah, I think that's about all there is to it. Mechanisms and electrophiles and nucleophiles, everything starts to really click and come together and make sense. So if there's any questions, though, please leave it in the comments below. I'd be so happy to help. And